Okay, good morning to all of you. Can you hear me? Can you hear me?
Yes, sir.
Okay. And I guess you can see my screen too, right?
Yes, sir, we can.
Okay, so um, what I want to do in today's lecture is to actually um, begin by just revisiting, reviewing what I did last time somewhat quickly. Um, I think I went through it a little bit fast, so it might be helpful to go through the stuff that I did last time and then point out, uh, you know, uh, the repercussions of this model. What can you do with it? How do people use it in experimental work? So, um, I think I can maybe go back to. So, our starting point uh, is the set of equations shown over here, which describe um, the manner in which these are just straight out of mass balances, describing the evolution of biomass, substrate, and the product uh, in a shake flask, in a well agitated shake flask, or in a batch reactor. And the first question that one needs to address before you can do anything further is to specify how does mu, Rs, and Rp depend on the concentrations. Only then do you get a well-defined system of differential equations. So I must know mu, Rs, and Rp in terms of x, s, and p. That's when the picture is complete, and you can move ahead with the solution of the differential equation. And the first attempt was made by Monod. He basically viewed growth as a single reaction in which a certain amount of biomass, which today we denote, he called it yield, it's basically a stoichiometric coefficient, which basically is called y-XS. The second subscript denotes the grams of substrate, and the first subscript denotes the grams of biomass. So taken together, y-XS represents the ratio of the grams of substrate consumed per gram dry weight of biomass produced. I should point out that some people don't use um, grams, they don't use mass units, they use molar units, and this is actually permissible because, as I pointed out to you last time, even biomass has a well defined uh, chemical composition. So, can associate in molecular weight with biomass as well. Maybe we will look at that later on, but for the time being, we just assume y-XS to be grams of substrate consumed per gram dry weight of biomass produced. And the rate at which this reaction takes place is, according to Monod, only a function of S. It does not depend on the amount of biomass you have. It depends only on the concentration of S. This has been modified later on, and we'll look at some of that later on, but these were the assumptions he made. And with these two assumptions, you basically get the picture over here. So in addition, he said that this function mu of S has the hyperbolic form mu m multiplied by S over Ks plus S, where mu m is called the maximum specific growth rate and Ks is called the saturation constant. Okay. So ultimately you have the rates you want. Mu of S has this particular functional form. Rs is simply y-XS times mu, which is equal to the full expression given over there. And later on, people found that other things also hold, but we then moved on, basically looking at the repercussions of this model by looking only at the evolution of the biomass and substrate. I'll ask you to do the same thing for product. What are the repercussions of this model? What does it imply? And that model is stated over here. It says that dx dt is equal to mu times x, where mu is equal to mu m times s over ks plus s, and ds dt is equal to minus rs times x, where rs equals yxs times mu. And you have some initial conditions, x equal to x0 and s equals s0 at time t equal to 0. And then I went on to tell you that initially the substrate concentration is very, very high compared to the saturation constant Ks. In fact, it's orders of magnitude higher, since Ks is on the order of 10 micrograms per liter to 10 milligrams per liter, whereas S0 is on the order of 1 to 10 grams per liter. And therefore, this ratio S over Ks plus S remains constant, is certainly equal to 1 initially, and it remains equal to 1 for a very, very long time until S is nearly exhausted. Okay? Under that assumption, we reduce the system of equations to the equation shown in red, which says that dx dt is equal to mu m times x, which simply says that actually that the cells are growing at their maximum specific growth rate. Notice the dependence of mu on s has disappeared. And then ds dt is basically minus yxs times mu times s. Okay? And this we solved. We found out that x of t increases exponentially as x0 e to the power mu mt. And the second thing I showed was that the change in S, the second equation, which is shown over here, x of t minus x0 equals ysx times s0 minus st. This is simply telling you it is converting the stoichiometric relationship between S and X into a relationship that we should expect, that the amount of biomass you produce, which is x of t minus the initial amount x0, must be proportional to the amount of substrate that you have consumed, which is S0 minus S of t. And the proportionality constant is nothing but ysx, where I should write down, because I have switched. So yeah, this I have shown over here. Notice that ysx is simply the reciprocal of ysx. So from the notation that we have devised, if yxs denotes the amount of substrate consumed per unit dry weight, then ysx is the amount of biomass produced per unit substrate consumed. So it's just the reciprocal of that. This notation makes sense. Okay, so this was the point at which we ended. Now, you can take it a couple of steps further. Simply, I'm going to actually solve for S of t in terms of x of t, right? Using this relationship over here. I already have x of t over here, exponential growth, and I'm going to solve for S of t by using the second equation. So S, the second red equation highlighted in red, implies that S0 minus St is equal to x of t minus x0 by ysx, which means that S of t is equal to S0 minus x of t minus x0 divided by ysx. This equation. And finally, substituting for x of t gives me this final result. Okay. One point to notice here is that according to this equation, so the solutions that we have obtained, notice that, I should point out here, so notice that our solution is such that x grows exponentially forever, right? And S of t, it can take, I should say, can take oops, all right. Can take negative values at large time. So let's just go back and take a look. We have said that x grows exponentially in that form. This means that x just keeps on growing and growing and growing forever, right? Now, if x grows forever, and I put it into this equation, you can see that at some point, uh, s will become negative. So it's pretty obvious what is the source of this sort of weird result. Can you see why? Can anybody take a guess as to why we are getting this weird result?
So maybe because we didn't specify a bound, like to the quantity of S.
Maybe take another shot at it. It's kind of it's an assumption we made very explicitly.
So that the biomass is actually we've defined the composition of the biomass basically.
Is anybody else willing to take a shot at it? Ratnesh, are you willing to take a shot?
No, sir.
Okay. So let me go back and so I mentioned that the specific growth rate is actually mu m times s over ks plus s. Actually, but we have simply assumed that this ratio is equal to 1. So basically we are actually not allowing S to influence specific growth rate at all, simply because our assumption is true at least up to the end of exponential growth. But will it be valid beyond exponential growth? And if not, why not? Let me draw. You can see the picture here, right? This is what I told you the data looks like. This is what the biomass concentration looks like. And in red is what the substrate looks like. At the end of exponential growth, S has actually fallen down to levels comparable to S. Can you now see what is the paradox? Why does X keep on increasing? Whereas you can see right here that the X actually plateaus out.
Yes, sir, it's clear.
What is the reason?
So because we assumed S over Ks plus S to be equal to 1. So basically after some points S would be comparable to Ks, and then basically the dx by dl would not be an exponential function. Like x would not be exponential basically.
So, I mean, the reality is that when S becomes comparable to Ks, this model is no longer valid. So, essentially, this model is no longer valid beyond this red vertical line. I mean, once S has fallen down to those low values comparable to Ks, our approximation, this model is valid, but our approximation mu equal to mu m is no longer valid. If, however, we keep on using the model in an obstinate way, well beyond the point where it is valid, we should not be surprised if we start getting weird results. So it should not come to you as a surprise that that's what's happening. We can only use it up to the point where S is in fact much bigger than Ks. So that is the reason why. Um, so the reason is. So the reason is that S say just say the model is only valid. The model is only valid when S is much bigger than Ks. It breaks down when S becomes comparable to Ks. So maybe so I then I want to move on. So however, that does not mean, as you will see, however, we can still use the model, as we will see in a numerical example. We can still use the model to approximate the entire growth curve. The entire growth curve. So basically, you're a bit clever. You can still use the model. So first I will show you the idea behind it geometrically. Geometrically, or meaning in the form of a visual, this is time, and this is, let's say, the log of x to the base e, which I will frequently refer to as ln of e, sorry, ln of x. Now, in reality, not in reality, but for the general model where we did not make any such approximation, if you integrate the full model out, it will basically show you something like this. This refers to exponential growth, followed by a gradual but very quick. Gradual meaning it's going to go like that. It's going to bend over and then become horizontal. But this will be like a smooth change. Whereas the model that we have drawn, actually, if I draw it in red, only goes like this. It only goes like a straight line like that. So what we know, as I'll show you in a minute, luckily for us, we can also estimate this maximum biomass level, which I am showing by a horizontal dashed line. What is this? This is what they call the maximum biomass concentration, which is attained during the stationary phase. Now, what is this maximum biomass concentration? Well, it's kind of easy to estimate. Why? Because we have found that x of t minus x0 equals ysx multiplied by s of t is s0 minus S of t. This was the relationship that we found. And we know that when is the maximum biomass concentration attained? What is the substrate concentration when the biomass concentration is maximum? Can anybody take a shot at it? In other words, I am asking, what is the value of this when you have reached stationary phase? I can see the people are rapidly disappearing since I'm asking questions. Anybody want to take a shot? Can you see why this might be approximately equal to 0?
Yes, sir. Like all the components, like nutrients, will be there. That will be consumed by the bacteria or whatever is there.
I think I actually drew the diagram. I actually showed you that if this is the profile of X, I actually drew a picture and showed you that the profile of the substrate is kind of like this. This corresponds precisely to the point where the substrate concentration becomes vanishingly small. That's what I pointed out to you. So now, if S of t is equal to 0, when X of t is equal to X max or Xm, what is the expression for X max?
So x naught plus ysx into s naught.
So X max equals X naught plus y Sx multiplied by S naught. So this is another important relationship. And the reason why it is important is that this tells us where to stop using the exponential growth, well, not exponential, the maximum, where to stop using this equation. You know, if you should never go beyond that point. You understand? So basically what we are going to do is we are splitting the actual model actually predicts what I have shown as the white curve, which I have labeled as X of t. And this red line is showing you what happens. This is the equation e to the power mu m of t, which hugs the original curve very, very closely up to that point, x equal to x max. But then beyond that, it kind of diverges. You know, our approximate solution will keep on going up, but the real solution will plateau out at x max. So, you know, we agree that we will not use it beyond x equal to x max. It makes no physical sense. Is that part clear? I mean, we're using it in a numerical example. So I should point out that actually, using the equations, you can get this exact solution. And at the end of the lecture, I'll give you the basic method for doing it. But the solution is so complicated. It has so many crazy functions in it that it is of no, intuitively it gives you nothing. And therefore this approximate or Jugadu solution is actually better for us than the exact solution. Is that part clear?
Yes, sir.
Okay. So now, before I proceed further, there is one more thing I'd like to point out, and that is I want to go back to this solution. X of t equal to x0 e to the power mu mt. Now, it turns out that, engineers like to use this, shall I put it? Exponential functions typically have the form a to the power x, where this is called the base and this is called the exponent. Now, one is actually free to choose any base one wants, right? Under certain conditions, actually, for most calculations, you don't use e, you actually use 10. It turns out that actually, from the biological standpoint, this base e is not a convenient base to have. The microbiologists actually use the base 2, and that gives a very easy interpretation to what is going on. So basically, instead of writing this equation as x equal to x0 e to the power mu t, they want to write it as x0 multiplied by 2 to the power something. So the base is not e, but the base is 2. So we want to see what happens when you do that. That gives rise to the concept of what is called the doubling time. So mu m, let me just emphasize here, mu m, so it should be clear that, notice, well, let's just say, so biologists, and actually you will appreciate it, that this is actually the right way to look at it. I prefer to describe exponential growth in terms of the base 2 rather than e. So maybe once again I'll show it to you as a figure. So if this is, let's say, how shall I put it? Let's just use z, neutral, and I plot, for example, e to the power x, e to the power z. So if this is 1, then e to the power z will look like this. This is 0. This is e to the power z. Now, if I have to plot 2 to the power z, then what will 2 to the power z look like? 2 to the power z, it will basically be below e to the power z, right? Because you remember e is approximately equal to 2.7, so which is bigger than 2. So that means that if you plot 2 to the power z, it will actually look like something like this. So this is 2 to the power z, which is always below. So for every z that you take, e to the power z is bigger than 2 to the power z. But what is interesting is that by a slight rescaling of the z-axis, you can make the two functions overlap. And why is that the case? That is the case because e to the power z is equal to 2 to the power z divided by log of 2 to the base e. This relationship is always true for all z. And why is that relationship true? Well, just check it out. Well, take the natural log of both sides. The left hand side will give you z of log e to the base e, and the right hand side will give you z divided by log 2 to the base e multiplied by log of 2 to the base e. This is equal to 1, and log 2 cancel out, which is also equal to z. So you get z equal to z. This is an identity. So what is the physical meaning of what I have written down over here? This relationship. Another way to see it is I've basically written down that e to the power z is equal to 2 to the power some z divided by some constant z bar. That means if you rescale the z axis, the 2 to the power z can essentially be mapped into e to the power z. That part clear? Actually, I'm just going to use this relationship now, this relationship over here, to show to you that we got the solution. We got the solution x of t equal to x0 e to the power mu m t. This is the solution that we got. But from this relationship above, we can write this as x0 equals 2 to the power mu m of t divided by log of 2 to the base e, which I can write as x0, so the biologist just basically, which is equal to divided by t divided by this quantity td, which is called the doubling time, which is related to what we earlier called mu m by the simple relationship td, the doubling time, is defined as log 2 to the base e divided by mu m. This relationship is also important. So this is the relationship. This is also important. This is just re-expressing what we got earlier on in alternative terms. So this is, now you can see here why TD is called the doubling time, right? When the actual time is equal to TD, you can see that x of t will be equal to 2 times x0. So it's obvious TD is called doubling time. Doubling time, it has units of hours because when t equals td, then x is equal to x0 times 2 to the power td divided by td, which is equal to 2 times x0. So this is the time in which x doubles. Is that part clear? So it's notice the difference between the units. Note that mu m has units of per hour, whereas TD has units of time, hours. So, it's a much more intuitive unit to work with instead of mu m. I mean, if I tell you that mu m for a particular strain is equal to 0.7 per hour, it means, at least to somebody like me, it means nothing. But if I tell you that the doubling time is 1 hour, which is actually the same thing, because it turns out that this log 2 to the base e, this quantity here, this is actually equal to 0.69, which is approximately equal to 0.70. So if mu m is equal to 0.70, you can see TD is equal to 1 hour. I can visualize something in my head when I say the doubling time is 1 hour. But if I say mu m is equal to 0.2, I don't know what the hell it means, to be really honest with you. So for me, somehow, this quantity, which the biologists work with, has a much more intuitive meaning than the quantity mu m. So I just wanted to point that out. I mean, in the engineering literature, they just keep using mu m, mu m, mu m. But the moment you go to the biological literature, they use the quantity doubling time. So if that part is clear, I'd like to go now to a numerical problem, which I will now share with you. So this is the problem that I look at. Problem 1. Can you see the screen?
Yes, sir.
Yes, sir.
Okay, it says that a microorganism is cultured in a 10-liter bioreactor, batch bioreactor, which is what we're dealing with, which initially contains 100 grams per liter of growth substrate. So actually, it should be, instead of growth substrate, what they mean is this is the substrate that will limit the final density that is reached. Remember, I told you that in shake flasks, you have so much substrate, on the order of 1 to 10 grams per liter in the environment, that the specific growth rate is more or less independent all the time. But the final density that is reached does depend upon, can be changed. If you take less of the carbon source, it will be the first thing that gets exhausted. So your final cell density, which I called X max, will be determined by the carbon source. Somebody else might come along and say, no, man, I want to do it such that the nitrogen source is exhausted. So then he will cut down on the nitrogen source. In this case, the final cell density will be limited by the nitrogen source. And in that case, what you will find is that when X max is reached, the nitrogen is completely over, but the carbon source is still there. Substantial amounts of it are left over because the cell stopped growing due to the exhaustion of the carbon source. So when they use the word growth substrate, they mean the substrate that ultimately limits the X max. What is the X max that is attained? Sometimes technically they call it crop limiting. What is the final crop of organisms that you get? Okay, so returning back to the problem, a microorganism is cultured in a 10-liter batch reactor, which initially contains 100 grams per liter of growth substrate, considered to be a high concentration. I want to highlight this because this is a relevant piece of information. I'll come back to this in a minute. So it initially contains 100 grams per liter of substrate and 0.2 grams per liter of biomass. So essentially they have given you S0 as equal to 100 grams per liter. This is the initial amount of substrate. And they have also given you X0, which is the initial quantity of biomass when you start your bioreactor. When you inoculate the bioreactor. Okay, so you are told by a colleague that the doubling time for this culture during the exponential growth phase is very reproducible with TD equal to 1.25. So they have given you the doubling time as 1.25 hours. After a total of 6 hours in culture, you measure the cell density and the substrate concentration and find that X is equal to 1.24 and S equals 7.73. So let me draw the picture here. Essentially, they are telling you, let's say this is your time, this is the time at which you started. Okay? They're saying that at this time, X was 0.2 over here. This is X0. And I'm drawing it in the semi-log coordinates, so X kind of goes up exponentially, and I guess at some point it finishes and reaches stationary phase. What they are telling you is that at t equal to 6 hours, so at t equal to 6 hours, this is 6 hours, the X had reached a value of 1.24. X is equal to 1.24 here. Now, if I also draw let's say, if I also draw the substrate concentration is, let's say, coming down like this. And it ends at precisely the point where the stationary phase is reached. They are telling us that the substrate concentration was 100 grams. So S0 is equal to 100 here. And at time t equal to 6 hours, at this point, S is equal to 73 grams per liter. Okay. Now, the first question asks you to find out the maximum specific growth rate, mu m. So, I think I'd like to do this a little bit interactively. How will you find out mu m?
So from TD, because TD equal to ln2 by mu m.
I actually, there is some, the voice is getting distorted. I couldn't hear you. Can you repeat?
So TD equal to ln2 by mu m. So we know the value of ln2, so we can find mu m.
Okay. So basically, the first one, A, is straightforward. A, you simply use the fact that the doubling time is equal to ln of 2 divided, sorry, it's the other way around. They're asking for the maximum specific growth rate. So I guess in this case, mu m is equal to ln of 2 divided by the doubling time. Okay? Anybody who has done the number, what it turns out to be?
0.55.
So this is 0.55 per hour. So an easy way to remember this is, like I said, the doubling time is 1 hour when mu m is equal to 1 hour. When the doubling time is 1 hour, mu m is 0.7. So if the doubling time goes bigger than 1 hour, then naturally mu m has to be less than 1 hour. What about B? How would you find out the yield coefficient?
Sir, we will determine first the biomass and then the substrate remaining after 6 hours, and then we can find.
Yeah, can you give me the formula?
Sir, I joined a little bit late, so I didn't hear like that.
Okay, anybody else? Is there anything here that we have done that will allow you to calculate the yield? scanning through the formula just in case. Do you spot anything here that you can use?
Yes, sir.
What is the
So we
formula?
can use this formula xt minus x naught divided by s naught minus st for calculating y as x.
Huh? I mean, it's y as x is equal to x t minus x0 divided by s of t multiplied by s naught. Well, we are given x at time 6. We are given x0. We are given s0. We are given x and s at time t equal to 6 hours. So we can find out what the yield is. Has anyone calculated that? Can someone give me that number? This is 100 minus 73 divided by, sorry, around, so
0.038.
1.24 minus 0.2 divided by, this is 100 minus 73, which is equal to 0.03. What was it?
So 0.038.
So that's so many grams dry weight per gram of the growth substrate. Oh, okay. Before I proceed further, does anybody see why they have specified considered to be a high concentration in the problem? The portion that I've underlined.
So probably because then we can use the assumption that mu will be equal to mu m.
That's right. I mean, without it, we cannot appeal to that theory. Supposing, if going back to the notes, if my at the starting point, if I could not hold this assumption, I couldn't do it the way I did it. If S0 was comparable to Ks right from the beginning, it would never hold on to the specific growth rate. This particular quantity would keep on changing. Because right at the beginning, S is on the order of Ks. So as S decreases, mu keeps on changing. That means if you plot the data on a semi-log plot, you will never ever get this. It'll be changing from the very beginning. You will get something like this. You simply cannot use this theory. Then you have to actually solve the exact equations. You cannot make the approximation. So it is only under this assumption that you can assume that it is attaining mu m for almost the entire period of growth. Okay, so now let's go back to the problem. The next question is, what is the maximum cell density xm reached at the end of, actually this is upside down, well, you can solve it. What is the maximum cell density xm reached at the end of the exponential phase? So they're asking you, what is the cell density when it goes all the way to the end, when the substrate gets over?
Sir, it will be exactly like the substrate growth, substrate concentration at initially substrate concentration.
I'm sorry, I'm actually. Can you repeat?
No, sir. It'll be.
Can you? No,
It'll
let's
be.
just give. Can you? Let me just understand what was said because I couldn't hear it clearly. Can you repeat what you said?
Sir, I said that it will be like exactly the substrate concentration. What is the substrate concentration initially? Yes.
So just give me a formula, right? Can you give me a formula for the maximum concentration?
So x naught plus y sx into s naught.
That's right. So C is x max is going to be the initial cell density plus y sx multiplied by s naught. This is derived right here. Right here. So I'm boxing the formulas. I don't know if I can do better than this. I mean, I boxed the formulas saying these are important. With the hope that it'll concentrate your attention on the important formulas. Let me now go back to problem. So what does this turn out to be? I mean, has anybody done the calculation?
100,
This will be
100.0076. 100.0076.
no, that doesn't sound right. Well,
So
x
4
zero
grams
is
per
how
liter.
much? X0 is 0.2, right?
I'm sorry. Yeah, sir.
And
Yes,
what is
so
y
0.2
sx?
plus 3.8
So this is 0.038
into 100.
multiplied by 100. So I hope you understand
That's
the
4.
physical meaning, right? This x max means that you started off with x0, and this ysx multiplied by s0 is giving you how much you made during the course of growth, right? Ysx is defined as how much x you make per unit s. Well, you had S0 at the beginning, so Ysx times S0 is what you get when all the S0 has been converted to biomass. So this is the new biomass created, and that should give you 4.0 approximately. So this will have units of 4 grams dry weight per liter. Okay. Now there is a reason why I made the figure the way I did. I didn't start off at t equal to 0. Notice the fact I made the figure, I left some space. Well, the reason is that it is possible that there was a lag time, but the person was not monitoring it. In other words, it is entirely conceivable that basically nothing happened for a period of time equal to T lag. So this is T lag. Some time between 0 and 6, actually no growth occurred. And then at time t equal to T lag, which is called the lag time, and the reason why this lag time occurs is that sometimes the cells need some time to adapt to the new medium. If you've grown the cells in say LB medium and you suddenly move them into glucose, then it takes time for them to build the machinery that is required to go on glucose as opposed to LB medium, because in LB medium you're supplying all the rich amino acids and everything else. But when you grow them on glucose plus minimal medium, then the cells have to make all these amino acids, and the time required to induce this machinery takes time. That's called lag time. Has this stuff been covered in your microbiology course? Lag time and so on and so forth, lag phase?
Yes, sir. Yes, sir.
Yes, sir.
Okay. So now, what is the lag time?
So in lag time, the cell prepares itself so for the growth phase, like.
So again, I would prefer, these are numerical questions, right? You are no longer doing biology, you're doing
For
engineering now.
this,
So we have
can I
only
go?
quantitative answers, no descriptive answers. I said at the beginning of the course, there will not be a single question involving describe this or describe that. These will be the questions that you will get. So start practicing. What is the lag time?
So we can take like the like 1.24, which is given at the end of 6 hours, should be equal to x naught into e to the power mu m into 6 minus t lag.
So shall I write it down? Repeat what you said.
So
X0 is what?
1.24 equal to
1.24 equal to
x naught
x naught.
into e to the power mu m
Uh-huh.
into t 6 minus t lag.
6 minus
T lag.
T lag. Where x naught is equal to what?
So it's given 0.2.
Uh-huh. So that's it. Basically,
Yes, sir.
you know mu m. You know. So essentially what you're saying is that you know what happened during these 6 hours, right? During these 6 hours, there was exponential growth, right? So this will actually, if you want, you can call this quantity TEXP. So you can solve for TEXP because it went from 1.24, it went from 0.2 to 1.24 during exponential growth at a mu m of 0.55. That allows you to calculate TEXP. This should be about 3 hours. Has anyone done the calculation?
So 2.706.
So D So D, oh come on, this is not working. I don't know. She stopped working. Uh, Stupid. So D says that TEXP, which is the exponential part of the growth during the first 6 hours, is essentially equal to 1 over mu m ln of I don't know 1 x of t divided by x0. I should actually say x of 6. That is equal to 1 over 0.55 multiplied by ln of 1.24 divided by 0.2, which I'm told is 2.7 hours, right? So once you know that the exponential part is 2.7 hours, that means this part that I have labeled this part is 2.7 hours. So what is T lag? 6 minus 2.7. That means T lag.
No, sir. The T lag is 2.7. Like after subtraction, it is.
Oh, I see. So this is 3.3 then?
Yes, sir.
So this is 3.3. So then that means that T lag is 2.7 hours. Is that part clear? What about the
Yes, sir.
last one?
It's clear.
The last one, the length of the exponential growth phase. This is actually straightforward.
It will be x max equal to x naught into e to the power mu m into t.
Just apply this formula now. Now the guy is basically saying, tell me the length of this portion. I'll show it in green. He wants this entire length. This entire length. Sorry, I didn't do it right. This length. the entire exponential growth phase. Well, we have already estimated x max. We have already know that when it reaches this point, we know what x is. So then use that x max to calculate. So t exponential, I guess put t bar to say the entire exponential growth phase is 1 over mu m multiplied by log of, now you won't put x at 6 hours, but xm divided by x naught. And how much does that come to?
So 5.4.
5.4 hours. So notice the fact that we have implicitly used what I told you. You see, we are only entitled to use this model during exponential growth. And you can see that the way we are doing the calculations, we basically use this model up until it reaches xm, and then we stop using it. That part clear? Can you see? Sit back and think about it. I guess what I'm trying to say is, I kind of tried to emphasize it when I did it here. This is the picture I drew. Basically, I told you that the white curve here is the exact solution of the model. Now, the exact model will plateau out at x max, and the reason for that is obvious, because in the exact model, the substrate will get exhausted. When the substrate gets exhausted, mu will start to decrease. So you can actually see that around the place where the white curve bends into a flat portion, that bending is causing the growth rate to come, the specific growth rate to come down. It must be going to zero. That's why x is flattening out. But our model doesn't allow that. It just keeps on allowing the cells to keep on growing. But the way we work around it is, put stated another way, our model is breaks down into two pieces. Maybe I'll show the other piece like this. So we follow the red line, and at x equal to x max, we switch over to the blue horizontal blue line. That is the idea behind this approximate model. So I hope that the picture is clear. Now there's only two more things I want to do. I'm sorry, I couldn't hear you. Did somebody say
Sir, can you please? Yes, sir. I am saying, sir, can you briefly this, what is method x max exponent and exponent?
I'm lost. I'm not able to hear you. Yeah, there's a lot of echo. And did anybody else grasp what the question was?
No, sir, I guess the voice is breaking.
Can you send me this question by on the chat or something? I mean, I'm not able to hear you.
Am I audible now?
Yes, you're audible now.
Sir, I was asking, like, can you briefly mention, describe what is x max, end of x growth phase? I was asking just this question. Not sure.
X max is the maximum, when you provide a certain amount of substrate S0 at the beginning, there will be a point at which the cell will stop growing. I mean, the maximum concentration that the biomass will achieve is determined by how much you have supplied at the beginning. So when they reach that maximum level, that is what is called X max. That X max will be X0, which is what you gave at the beginning, plus the additional amount YSX times S0 that you created during the process of growth. That clear? Oh, I'm not able to hear you. Maybe we can do this offline. I mean, I can't hear you now. You can put your inquiry, you can put your question as a form of a chat, and I'll address it later on. So I want to go on now. This is again related to the questions that I'll be asking you later on. So this is experimental determination of the two parameters of mu m and ysx. I should also mention, but not ks. So it turns out that you can. This is actually probably the most frequent experiment in this area. At the moment you get a strain, the first thing you do is you characterize this and this. You characterize the maximum specific growth rate, and these are so characteristic of the organism that the moment you have these two numbers, it's as if you have their first name and their last name, right? This is their identifying feature. And later on, you can often check whether the cells are mutated by checking these. If these have changed, that means your strain has mutated or your reactor has contamination. So this is an extremely important. Now the question is, the main point I want to make is that you can measure mu m and ysx, but there is no hope of getting ks. So if I can go back to the original model, I said that there are actually, if you go back to the original model, there are actually not two but three parameters. There's mu m, there is ks, and then mu m and ks characterize the specific growth rate, and y-axis is another parameter that characterizes the relationship between the substrate uptake and growth. So you have three parameters, but this shake flask or batch culture is just inherently incapable of giving you KS. And the reason why it can never give you KS is that basically the cells are growing at mu equal to mu m virtually all the time. The influence of KS is felt only in that very short time period when they transition from exponential to stationary phase. So in that short period of time, which lasts like maybe 2 minutes or maybe 3 minutes, you just can't get any data to sample the effect of KS. So, you will actually see some people uh, presenting methods for determining KS. I think that's the biggest load of crap I've ever seen, because it's just impossible. If you don't have data, how can you measure the parameters? But mu m and ysx can be pretty simply measured. And of course, the determination, the first one, mu m, let's start with mu m. This is, of course, pretty straightforward, right? I mean, just plot. You got the data. So you got essentially, you measure actually what is called the optical density at, it's called OD 600 if you are measuring it at 600 nanometers. From the optical cell density, you can calculate how many grams dry weight you have per liter. So I'm assuming that you have a temporal profile, so you have some points. Now you take the log to the base e of x and plot it here. So you're plotting log x to the base e, and I just told you it should be a straight line followed by a horizontal line. Now it's pretty straightforward, right? I mean, according to the model, we have dx dt equals mu m times x. Basically, this slope is equal to mu m. So just take the data, your data, and confine your data to the part corresponding to exponential growth. Make sure you do not take points from the stationary phase. I should also point out one more thing. Frequently, as I mentioned, you can actually get what is called a lag phase. If you don't do the experiment properly, you will actually get something that looks like this. So one thing is to eliminate the lag phase, but that's problematic. The other is to basically do the experiment in such a way that you do not get a lag phase. And the way to do that is, supposing you take the cells out of the freezer, they've been stored. First, you grow them on LB medium so that these cells, can recover from the state of hibernation they were in the freezer. You then first, let's say you want to see their growth rate on glucose. Now, first you grow them on glucose for one culture. Let's say you expose them to glucose for about 5, 6, 7 doublings. Now they're fully accustomed to growth on glucose. Then you take these cells from glucose and then start the experiment again with a third culture where they're exposed again to glucose. Now, since the cells have already seen glucose in the previous culture, they start fully trained and you will not see any lag phase. So you just eliminate it. This lag phase will not occur at all. This will not take place. So you get pure exponential growth. Just find the slope of the semi-log plot and that will give you mu m. That's your experimentally measured value of mu m. Is that part clear? There's not much to it, right? Is that straightforward or should I repeat it?
So it's clear.
And the second one is the parameter YSX. Well, this is also an important one. Well, there are two ways to measure this, right? One is, and to me this is the easy one. We know that. Let me go back and show you the relationship. It's right here. This one. So this relationship says that the change of x divided by the change of s is equal to minus sx, minus ysx. Well, what I do is, essentially, I am collecting data, I am measuring both x and s. So I'll show you. I also have, example, collected the data for s. And this I am showing here. So at the same time point, I have collected not only the cell density but also the corresponding substrate concentration. So I have in hand x of t and s of t at various times. This is how I am doing my experiment. Now all you do is basically plot. Come on. You plot your various time, so here you plot x of t and here you plot the corresponding s of t. So essentially at the beginning, you will have lots of substrate and very few cells, right? That's how the experiment begins. You can see on top, you start with a small quantity of cells. So you will have a point here. Then after some time, the substrate concentration will come down, but the cell density will go up. So you get another point here, then another point here, then another point here, then another point here. Well, and the model tells you that this should be a straight line with slope equal to minus y sx, because as I just told you, dx ds is equal to minus y sx. To exploit this relationship, to get YSX. This is one way to do it. Another way to do it, which is somewhat, which was used in the olden times, it's somewhat crude. Now that's a method you can use if you don't have any. So in the olden days, they could not measure S. Now, this new technology for measuring S rests upon the availability of what is called chromatography, liquid or gas chromatography. And these machines actually spit out, within 10 minutes you can find out how much sugar or how much ethanol you have in your medium. But this was not available in the good old days. And there they exploited not the relationship dx ds equal to minus ysx, which requires both x of t and s of t. They could only measure x. Well, what they did was they exploited the relationship x max equals x0 plus y sx s0. Now, how did they use it? Well, if you take a look at the experiment, you will see that in most experiments, this is x0 and this is the maximum value x0 plus ysx multiplied by s0. So you've gained ysx s0 biomass as you jumped up. Well, it turns out that actually in most experiments, the second term ysx times s0 is like 10 times or 15 times the size of x0. Massive growth takes place. Start with a really, really small amount. You start off with like 0.02 and go all the way to 1. So that means that this term x0, x0 is very, very small compared to the actual growth that you accomplish. So this is actually equal to approximately ysx times s0. Now this tells you a simple way to measure ysx. Basically, do the experiment with different S0 and find out the X max in each experiment. They'll be proportional to each other. Okay, so this is X max. It'll be passing actually almost through the origin because we are making this approximation that X0 is much, much less than YSX times S0. So the slope of this will give you YSX. Now, I should point out that this method is a little tricky. You should not allow your S0 in this experiment to become so big that something other than your substrate of interest becomes limiting. So, for example, if glucose was your limiting substrate, right? Now, you should go only 2 to 3 fold. You should not increase the level of glucose by a factor of 20. Because if you do that, then maybe at large enough S0, if you have like 20 times the amount of glucose you had, then maybe somewhere here, actually, something else is getting exhausted and your graph actually becomes not a straight line passing through the origin, but a piecewise linear curve that first increases and then increases horizontally, where this horizontal part is actually reflecting this horizontal part is where something else is limited. Is that part clear? I think we've already crossed the timeline, so I need to end it. Did you get the basic idea?
Yes, sir.
Yes, sir.
Yes, sir.
Okay, so then I will be posting these questions on the web. You can try to solve them now. I think they cover whatever you're supposed to do, meaning numerically. And in the next lecture, we'll move on to the next topic. Okay? All right?
Sir, on Moodle.
Yes, I will be posting it on Moodle.
Okay. Thank you, sir.